So we have formed the Earth now. The Earth is still cooling, it's still being hit by meteorites occasionally. Now we need to form a few other important things. We need to create an atmosphere, we need to create the ocean, and then we need to populate the Earth either via the ocean or by some other means. So for the next little bit now, we're going to focus on the creation of an atmosphere. We're going to focus on how oceans initially began and focus on how life started on the planet as well. The first thing that we're going to look at is at the atmosphere. We need an atmosphere. We need to breathe. And as we see, organisms that live in the ocean need to breathe as well, either by coming up to the surface to take big gulps of air, or what they can do sometimes is extract oxygen from seawater. The first atmosphere that we had was mainly hydrogen and helium. So H for hydrogen, He for helium. And this atmosphere didn't stick around for very long. It was basically stripped away. And it was stripped away by solar flares that were emitted from the very young sun. One of the things that helps our atmosphere stay in place today is the fact that we have a magnetic sphere or magnetosphere that surrounds the Earth. Remember that just a few slides ago we talked about how the Earth is density stratified with iron in the middle. What we find is this basically makes the Earth a gigantic magnet. And this magnetosphere helps to hold in the atmosphere. In the early Earth, especially the Earth prior to that bombardment that caused the density stratification that resulted in the formation of that iron core, we did not have this magnetosphere, and we didn't have this ability to sort of hold our atmosphere around our planet. Second atmosphere, by this time we had a magnetosphere. This helped hold everything into place in terms of the atmosphere. The second atmosphere, though, was something that we as modern day humans could not live in. It was an atmosphere that mainly consisted of CO2, carbon dioxide, and water vapor. This atmosphere got its start. It was basically burped to the surface. So when the Earth was formed, gases were trapped beneath the Earth's surface within the interior of the Earth, and eventually these get burped to the surface. Volcanic eruptions are a good example. Not only do we have magma coming up and being extruded onto the Earth's surface as lava, but we also have this process known as outgassing. This pouring out of material of gases, including water vapor, sulfur-based gases, nitrogen as a gas, hydrogen as a gas, water vapor as well, steam, that's a gas. This all comes out as part of a volcanic eruption. So in the early Earth, we saw that it was very volcanic, and we basically had this burping out of the Earth's atmosphere. The other important thing to remember here is that these gases are hot. We know that things have to heat up in order to move from being in a solid phase to a gaseous phase. Material that is hot in a gaseous phase will typically rise, and as it rises, it cools down and condenses into clouds. It's believed that this occurred roughly about 3.5 billion years ago. The final thing I'm going to say about this, if we were to visit the Earth at this time and look at the atmosphere, would see that it's very similar to Venus's present-day atmosphere, which has approximately 96.5% carbon dioxide within its atmosphere. That was Earth's second atmosphere, and you'd find that it was an atmosphere that was very inhospitable for us, for life. What we need to do is we needed to go from a second atmosphere to what is now the third atmosphere, the atmosphere that we live in, the atmosphere that has oxygen in it, high levels of nitrogen, as well as other components. We still have carbon dioxide present, but nowhere near as much as was present in that earlier second atmosphere. We went from what was initially called a weakly reducing atmosphere now to a strongly oxidizing atmosphere. This is why we see stuff with iron in it rusting. So what was the driving factor that led the Earth to go from the second atmosphere, something that we couldn't live in or survive in, to the third atmosphere? We'll take a look at that in the next slide. What happened to go from the second atmosphere to the third atmosphere is something that geologists call the Great Oxidation Event. At some point in the Earth history, there was the presence of cyanobacteria. All of a sudden, life appeared on the planet, life appeared in the oceans, and with this, we had cyanobacteria who had the ability to take carbon dioxide out of the atmosphere and convert it through photosynthesis to oxygen. So with the appearance of some of these early forms of life, cyanobacteria, for an example, we now start to see the huge amounts of carbon dioxide that are present in the Earth's second atmosphere being converted via photosynthesis into oxygen, air that is conducive to life as we know it on the planet now. If you look at this little graph here, this little chart here, we can see how the atmosphere has changed over time. We started off very early on in the Earth history with an atmosphere that first atmosphere, there was just hydrogen and helium. We then moved to an atmosphere that was dominated by carbon dioxide, water vapor, and other gases that were basically belched out by volcanic eruptions. And then finally, following the Great Oxidation Event, we have our modern day atmosphere. Levels of oxygen have changed throughout the geological past, but they've remained on average fairly consistent. We now have the Earth. We've created an atmosphere. The other thing we need to do now is to create the ocean. And the creation of the world's oceans probably first initially started during the second atmosphere. What happened is, during that belching of material through the Earth's surface that formed that atmosphere, we had a lot of outgassing, and as I said in a previous slide, we had the formation of clouds. These gases were hot, they would rise up above the Earth's surface, where they would cool, condense, and create clouds. And we know what happens when you have clouds. If there's water vapor in a cloud, as it cools and condenses, it forms rain. This eventually led to the creation of the first ocean. We had rain clouds forming high in that second atmosphere. Raindrops would form, they would start to fall, where they would collect on the surface of the planet in depressions, and this would be the initial stages of what would become the world's first oceans. This, once again, is an artist's depiction of what it might have looked like on the early Earth as the oceans were being formed. So these gases being belched to the surface, once again, contain water vapor. This hot steam rises up into the atmosphere, condenses into clouds, cools, forms droplets, and eventually have sort of this hot rain falling to the Earth. The Earth, though, at this point still is very hot. The surface is still warm. We have started to form a solid crust, but there's still a lot of heat. It takes a high temperature to melt rocks. So this rain would fall back to the Earth, collect in depressions where it would heat up, boil again, rise, cool, condense, and then fall back to the Earth again. And this cycle would repeat itself over and over and over again. It's a long process. It doesn't happen overnight. But over millions of years, the first oceans of the planet were created. This is what the surface of the early Earth would have looked like. Here we see many volcanic islands. The continents, as we know them today, haven't formed yet. We see that the sun is fainter than it is today. The sun, still very young in its life cycle, faint. It's estimated that it was about 80 to 85% as bright as it is present day. We have an atmosphere. We haven't had that great oxidation event occur yet. So the atmosphere is very similar to that of Venus. We see a lot of water vapor in it, a lot of carbon dioxide, sulfur-based gases, nitrogen, and we have, as I said, an ocean present. And this first ocean, it's believed to have appeared somewhere between 3.8 to 4.2 billion years ago. Geologists still haven't quite nailed down that time when the ocean first appeared. The other thing that we see here, and we'll talk about this next, is in this image we'll see some of the earliest forms of life. These life forms that led to the oxygenation of the Earth's atmosphere. So now we're going to leave behind the atmosphere, the ocean. We've created both of these, and we're going to talk about the populating the oceans. How did life begin? How did we get life into the oceans? How did we populate the oceans? Well, we basically have a recipe here for the creation of life. And we see that sort of four main things that we need. We need to take simple organic molecules. These are molecules such as our amino acids and nucleotides, and we need to have the ability to combine them into more complex molecules. We need the ability to either replicate or reproduce these molecules, and as we've seen over time, that another important component is to have water present. So we need these sort of four things to happen on the Earth to create life and to populate the oceans. The first thing we need to create life is we need to take or obtain simple organic molecules. And there's a couple of schools of thought of where the source or what the source of these organic molecules might be. Some people believe that they came from space and that all life on Earth could be considered alien. Other people believe that conditions were right on the early Earth that we could actually create these simple molecules, these simple organic molecules on the Earth at the time. The believers that think, or the people that think that life has its origins, these simple organic molecules have these origins in space or came from space, point to something called a sugar meteorite. So we have meteorites that come to Earth all throughout the year. A lot of them we're not aware of, some of them burn up into the atmosphere, but some make it through the atmosphere quite large, and we're able to collect pieces of these. We see that meteorites have a variety of compositions, but there's some that are known as sugar meteorites. And we see that these contain amino acids and sugars. Amino acids and sugars are important because these are some of those simple organic molecules that we use combined to create more complex organic molecules. We see that they're essential. They can create backbones of DNA and RNA, and they also can act as an energy source. So we do have meteorites, and this is a picture of one right now, as we call it, a sugar meteorite, that does contain some of these initial things that we need to create life in the ocean. Other scientists hypothesize that these simple organic molecules were able to be produced on Earth, that these building blocks, the conditions were ripe on Earth to create these organic molecules such as amino acids, such as nucleotides, such as sugars. So the next slide, what we're going to do is take a look at a very simple experiment that was carried out to prove that, maybe it was possible that these early simple organic molecules were formed early on in the Earth's history. So the Miller-Urey experiment was published in 1953, yielded amino acids. These are scientists that worked at the University of Chicago, and what they did is they wanted to prove that on Earth, near the shore, so once again in the ocean but near the shore, the conditions were sufficient enough to create these simple organic compounds, these amino acids and these nucleotides, these sugars. So what they did is they tried to recreate the early Earth conditions, both within the ocean as well as the early atmosphere. They set up this experimental apparatus. You can see it in the image to the right, where they had an area, a flask that simulated the early atmosphere, an atmosphere that contained water vapor and carbon dioxide. Another area, they were able to simulate the early ocean. And what they did was they basically heated up the early ocean. It rose up as gas, as vapor, water vapor, as steam. That entered the early atmosphere there. Within this early atmosphere, they passed through an electrical spark. This was supposed to recreate lightning in the Earth's early atmosphere. And then from that, they cooled everything down, sampled and analyzed the ocean water sort of in that lower part of their image there. And what they found out was they had created amino acids. So this experiment proved that it was possible on the planet to create these simple organic compounds. And even today, this question still is debated. Did these simple organic compounds come from space, or where did we create them on the Earth, as we saw in the Miller-Urey experiment? So we've taken these simple organic compounds, we've created these simple organic compounds. Then they're either from space or they're from building blocks we created on Earth. Then what we need to do is we need to combine them into complex molecules. There are many theories out there of how these simple organic molecules became combined into complex molecules. After we did this, we needed them to replicate and reproduce, and then we needed water. Obviously, we're looking at a lot of this happening in the ocean, so it makes sense that this is sort of a no-brainer. The water was there. We've met all the conditions of the recipe. We have our simple organic compounds, we have our complex organic compounds, we have replication and reproduction occurring, and we have water. So where do we think that life actually appeared? And more we're believing that life first appeared in the ocean, probably most likely at hydrothermal vents. These are vents that occur at some locations in the ocean. They were first discovered in the 1970s. And what we see is they're essentially volcanic vents from which really hot heated water is extruded. We have steam associated with this. These are known as black or white smokers, and high water temperatures. Hydrothermal vents are a really unique community, a biological community. We find organisms there that we don't see anywhere else on the planet or within the ocean. So it's an environment where very unique forms of life can live and exist and thrive. And this might be one of those things that make it a really ideal candidate for where life first occurred. So why hydrothermal vents? Well, one of the reasons is it's protected from meteorites hitting the ocean surface. So during this time, we're still developing that second atmosphere. We still have a lot of debris in space. We still have a lot of material that's falling from space onto the planet. And what we see is that as meteorites hit the planet, we start to have a boiling away of the top 50 to 100 meters of the ocean. So we had life, and life was trying to form in the upper surface of the ocean. It would have simply boiled away. Hydrothermal events typically occurred at much greater depths, so they would have been protected from this boiling away of the top 100 meters or so of the ocean. The other reason is that conditions are ideal at these hydrothermal vents. What we see is a range of temperature conditions ranging from near freezing, almost adjacent to the vents, to very hot temperatures where the water is emitted from the vents as well. We actually see in modern day hydrothermal vents that we have very primitive organisms living there. These are really hot waters, very acidic waters, and we see that very primitive, very basic forms of life thrive in these sort of conditions. So we have conditions where organisms live today under less than ideal settings that we wouldn't be able to live in. It's possible that these early forms of life too would have thrived in such a setting. These organisms are known as extremophiles. Extremophiles are organisms that live at vents. They live in extreme conditions. In this case here, they're able to metabolize sulfur. And what you see here in sort of the lower inset image is you see that red arrow, and that arrow is pointing towards small bits of bacteria that are living in these conditions. So it seems like this is a place that early life could have thrived, lived, and done quite well for itself. Life evolved in the oceans fairly on in Earth history, and here we see sort of the spiral, the history or the life history on the planet, way sort of in the lower right-hand corner. We see that life first appeared and very quickly diversified to become all the different forms of life that we see present on the planet today. There is a lot of debate over when life first appeared on the planet. We can pretty confidently say that the planet appeared somewhere about 3.6, 3.8 billion years ago, but we find that geologists and paleontologists are constantly finding new purported fossil evidence that pushes this date back further and further. Some of the fossil evidence that's found consists of chemical fossils. These aren't actually a fossil itself, but we see the signature of, for example, carbon, a type of carbon that can only be produced by biological sources, that exist within these rocks. So you look at a rock, you analyze it, you analyze its chemical components, you see this form of carbon, you say, hey, this had to be produced by a biological organism. If you know the date of the rock, you know the age of the rock, then you can say, yes, there must have been life present at this time. We also see microfossils. These are fossils, once again, in rocks that we know the age of. And we see that these are these tiny little fossils, evidence of early life. Finally, we see the presence of stromatolites. And stromatolites are a really unique fossil. What they are is they're not the fossil itself, they're not the organism itself, but it's a layered sedimentary rock. And these are formed by the growth of cyanobacteria. What happens is cyanobacteria, we know that this appeared fairly on in the Earth history, grew in shallow warm seas. As it grew, it was able to, was sticky on the outside, kind of had this mucousy cover. Bits of sediment that was present in the water would stick to the cyanobacteria. The cyanobacteria are photosynthesizers. They need the sunlight. So they would grow up and then would have another layer of sediment sort of coating the cyanobacteria again. This would repeat itself over and over and over again until you sort of get this layer upon layer upon layer upon layer of sediment. The cyanobacteria would die, the sediment would remain, it would be lithified, it would become a rock, and we're left with stromatolites. Stromatolites appear very early on in Earth history, and we still see them present in certain select locations on Earth today. Back to this image again of the early Earth, and now what I've done is I've circled some structures that are out there in the early ocean. They kind of look at like these circular blobs, and these are old stromatolites, these ancient forms of life that would have been some of the organisms that were responsible for the great oxidation event that created the Earth's third atmosphere. So there's strong evidence that life originated in the oceans, and it makes sense. Conditions were good for the creation of life. The components, the things that we needed to create life are present in the ocean, and the ocean presented as sort of as a protected place in which life could evolve and flourish. Stromatolites, one of these early forms of life that we see. We still see them today on the planet. Here's an image of modern day stromatolites. These are present in Shark Bay, Western Australia. And we find that they're really restricted to very warm waters, saline-rich waters that have very few predators, very few organisms that come and graze on the algae that create these stromatolites.